Welcome back to Business Calculus. This will be the lesson for section 3.3. The homework and quiz number 8, which cover 3.2 and 3.3, are due on Sunday, March 29th at 11:59 p.m. This section has to do with graphing rational functions and using asymptotes to graph those rational functions. We've actually seen some of this material before, but we'll look at it from a little bit different perspective today in this section. So we start off by talking about what a rational function actually is. A rational function is basically a fraction where we have variables in at least the denominator, maybe in the numerator and the denominator, but they must at least be in the denominator to be considered a rational function. Typically, it's some type of polynomial in both the numerator and denominator. What we do have to be careful of is any values which make the denominator 0. And so when we talk about the domain of that rational function, we're going to remove anything that makes the denominator of that function equal to 0. We'll see that when we get to these actual functions in a minute. So we talked about at the very beginning of this semester limits that ended up at infinity. So the limit as x approaches some value from either the left or the right. If I end up in infinity or negative infinity, these were some special types of things that we ran into back at the beginning in chapter 1. But what we can talk about now is that when we have these, what we call infinite limits, then we actually have what's called a vertical asymptote. Now, a vertical asymptote is a vertical line. It's not usually part of the graph, but usually sometimes when we see it in the graph, it's represented with a dotted line. This is a graph that the line gets very close to, but it's not going to cross. It is always written in the form of x is equal to some constant. So as we find these limits that go to infinity or negative infinity, the value that they approach is actually the value of x, which makes our vertical line. Remember, a vertical line from algebra is x is equal to a constant. So we're going to make this really very nice in terms of finding these, and we're going to talk about the limits where x goes to some value is actually going to be the value that we find by taking the rational function, simplifying it, and setting the denominator equal to 0. There we go. You can see that now. So we'll simplify the rational function. We'll take that denominator after we've simplified it. We'll set it equal to 0, and that's going to give us our vertical asymptote. So that's kind of the short and sweet way to do it. We could do a lot of other stuff, but that's really the easy way to do it. And that's kind of what we're looking for right now. So let's look at these problems. So this first rational function, f of x, is equal to x plus 4 over x minus 2. I can't simplify this. They're both to the first power, so I can't factor it. I can't divide anything out because I have terms that are added and subtracted. And so since it doesn't simplify, to find that vertical asymptote, so to find the vertical asymptote, and I'll probably start abbreviating this eventually. Asymptote is one of those words that I have to think really hard to spell. We take the denominator, x minus 2, we're going to set it equal to 0, and we're going to solve for x. And so x is equal to 2 is my vertical asymptote. That equation, and you do have to write it as an equation, so it must be written as an equation. So if you have a fill-in-the-blank question on your test or quiz, make sure that you write the vertical asymptotes as an equation. All right, so be really careful there. All right, let's move down here to number 2. Once again, we're looking to find the vertical asymptote or asymptotes of this equation, of this function. We have 5x over x squared minus 25. Now be very careful. I can't simplify the 5 and the 25 because this 25 is subtracted from x squared. However, I can factor this, and so I'm going to factor this denominator. The numerator doesn't factor, it's 5x, and this denominator does factor into x plus 5 and x minus 5. Again, however, though, there's nothing to simplify, and so in order to find those vertical asymptotes, I'm going to actually take two denominators, the two factors in the denominator, and so this one's going to have two vertical asymptotes. So I'm going to take x plus 5 and set it equal to 0, and I'm going to take x minus 5 and set it equal to 0. We really don't care about what happens happens in the numerator of these functions when we're talking about vertical asymptotes. So I'm going to subtract 5 from both sides, and I get one vertical asymptote of x is equal to -5. I'm going to add 5 to both sides, and I get a second vertical asymptote of x is equal to +5. So here are my two vertical asymptotes. One more problem where we have an x plus 2 over an x squared plus 6x plus 8. This is my rational function, again with variables in the denominator. This one I can factor. The numerator does not factor, but the denominator does, and so as I look to factor that denominator, I'm going to remember skills from algebra. This one's not the difference of two squares, so it requires a little bit more work, but it's not too bad. Plus at the end tells me I have two of the same sign. Plus in the middle tells me both of the signs are positive, so plus and plus. Factors of 8 whose sum is 6. As I was saying, factors of 8 whose sum is 6 are going to be 2 and 4. So now I see that I have a factor of x plus 2 in the numerator and x plus 2 in the denominator, and these will simplify. So that's what we mean by simplifying the rational functions first. And so now my function, the simplified version of my function, so the simplified, be sure to simplify before you do anything. So the simplified f of x is going to be 1 over x plus 4. So now I take that x plus 4, so now I want to find the vertical asymptote. In this case, I'm only going to have one because there's only one factor. So I take x plus 4, I set it equal to 0, and I get x is equal to -4 is my my only vertical asymptote for this function. Now this x plus 2 has some other implications. We would have problems with the domain of this function, but for right now we're only looking at the vertical asymptote. So be sure to simplify your rational function first. Anything that remains in the denominator that has a variable, we're going to set it equal to 0. X is equal to that number. That gives me my vertical asymptote. So the other type of asymptote that we have, remember an asymptote is this imaginary line or kind of a dotted line on our graph that a graph gets close to, doesn't necessarily cross, but we can talk about horizontal asymptotes. Notice that it is going to be in the form of y is equal to a constant. Our horizontal lines, remember from algebra, or y is equal to a constant, some type of equation there, but we find horizontal asymptotes if the limit as x either approaches -infinity or +infinity for a function is equal to that number. Now, shortcut kind of nice way to do this, and we talked about those limits to infinity back in chapter 1, but we'd also talked about the fact that we could do it a little bit of a shortcut. Horizontal asymptotes can happen if the degree in the numerator is less than or equal to the degree in the denominator. And so we're going to be looking at that. If the degree of the polynomial, whatever we happen to have in the numerator, is greater than the degree of the denominator, then we have no horizontal asymptotes. So let's look just a little bit here. Remember that if we have this x approaches positive or negative infinity of something to a power, that power is larger than 1, then we're always going to get 0, 1 or larger. So that's kind of where we're going from this. So, but the short way is this part right here. So that's really what we're going to be using. So let's look at this first one. Our rational function is 6x over 8x plus 3. Once again, we're looking for the horizontal asymptotes. Horizontal asymptote is going to be a y equals to something equation. So that's what we're trying to find. Remember, if we look at this, we can see that x to the first power is in the numerator, x to the first power is in the denominator. So since those are the same, we can remember that we simply take the coefficients of those x's, and so we can think about this as the limit as x approaches infinity. This kind of ties it into what we did at the beginning of the semester, and these are the values we're looking at. So since the power of the numerator and the denominator are the same, then we say that this limit is actually equal to 6/8, which will simplify to 3/4. And this becomes the magic number. So the vertical asymptote here is going to be, remember, be very careful. This is y equals 2, and it's going to be 3/4. Okay, so we'll put a little star here. So this is my equation. Y is equal to 3/4. This is your horizontal. I did say vertical asymptote, didn't I? I apologize for that. It's already been a long day. So this is our horizontal asymptote. So I promise to be very careful on the next one. So our horizontal asymptote is y is equal to 3/4. Thank you for your patience. All right, so number 5 here, we're trying to find again the horizontal asymptote of this function. So I have 4 times x over x squared minus 3x. Go back real quick. We're going to go back to this previous slide. The degree of the numerator is less than or equal to the degree of the denominator. So what is the degree of the numerator? The degree of the numerator is 1. The degree of the denominator is 2. And so is the degree of the numerator less than or equal to the degree of the denominator? And the answer is yes. So we do have a horizontal asymptote, remembering that that horizontal asymptote does come from that limit to infinity of 4 over x. Once again, kind of tying this back into what we did at the beginning of this semester for multiple reasons, but one, because you will see this on your final exam. So since my highest power of x is in the denominator, then we say this limit to infinity is, you remember, 0. And so this reminds us, or this tells us, that our horizontal, I promised I'd get it right this time, our horizontal asymptote, I'm going to abbreviate this one, is the equation y is equal to 0, and that is our answer for this particular problem. So again, the degree in the numerator is smaller than or equal to. Here's an example of equal to. Here's an example of smaller than the degree in the denominator. We always look for the highest power. That's another way to say that. All right, one more of these, and this one's a little bit different because it's kind of split into 2 pieces. We have just this whole number part here, and then we have the rational part here. So in this case, we're going to look at this a little bit separately, but still thinking of that limit as x approaches infinity for this function. So when we think about this, it's not terribly mathematical to say this, but this limit, this part of this limit is going to be 4, and then plus as x approaches infinity. So here's another case. The degree in the numerator is 0, degree in the denominator is 1, and so that infinite limit is 0, and so we say that this limit is actually 4, and this leads us to the fact that our horizontal asymptote is the equation y is equal to 4. Okay, so again, for these horizontal asymptotes, I'll write it out, must be written as an equation, So please make sure you are very, very, very careful on that, especially for fill in the blank types of questions, right? All right. So one more of these. So I'm looking here and I see that the degree in the numerator is, yes, 3. The degree in the denominator is 2. Is the degree in the numerator smaller than or equal to the degree in the denominator? And the answer is no. So if I were to think about this in terms of the limit as x approaches, and it can be either positive or negative infinity, most of us just like the positive one better. If I were to look at this and ask you to find this limit, then hopefully you remember from earlier in the semester that this limit, yes, you've got it right, does not exist. And so we say then that there is no horizontal asymptote, right? And so we would be done with that problem then. Okay, so if the degree in the numerator is larger than the degree in the denominator, that infinite limit does not exist, and therefore we say that there's no horizontal asymptote. All right. So we have a couple of just different types of functions. We've talked about exponential and logarithmic functions, and for these exponential and logarithmic functions, just a couple of rules apply. So as x approaches negative or positive infinity, these exponential functions always approach 0, and so we can say that for any of these basic exponential functions, they will have a horizontal asymptote at y is equal to 0. Okay, they don't have a vertical asymptote. For the logarithmic functions, our natural logarithmic functions, the natural log of x minus a is going to have a vertical asymptote at x is equal to a. So you take what's inside here and set it equal to 0. Okay. For this one, when we have a minus x, it's going to also have a vertical asymptote at x is equal to a. This is going to happen as x approaches that value from the left-hand side. So for the functions where I have a constant minus x, then the graph is going to be to the left side of that vertical asymptote. For my natural log functions where I have x minus my constant, my vertical asymptote is going to be what happens as x gets close to that value from the right hand side, so my graph will be to the right hand side of that vertical asymptote. We also looked a little bit at those vertical asymptotes when we graphed those natural log functions a couple of weeks ago. So not spending a lot of time on these, but a little bit, okay? All right, so we'll refer back to this as we go through some of these. So if I wanted to find the horizontal or vertical asymptote, so let's think about this for just a second. What did I just get through telling you about natural log functions? They have, we'll go back, so you can go back or you can pause and go back, or I'm going to refer back here. So logarithmic functions, our natural logarithmic functions, have vertical asymptotes in the form of x is equal to. So here we go. So that means no horizontal asymptote. Okay, we have x plus a number here, so our x comes first, and so that means that our vertical asymptote, we're going to take x plus 7, set it equal to 0, so we're going to have x is equal to negative 7 is our vertical asymptote for this natural log function. Okay, for our natural exponential function, real quick, we'll flip back here. Our natural exponential function has horizontal asymptotes of, you guessed it, y is equal to 0. We have a positive number to the times x for my exponent, and so therefore we have no vertical asymptotes, but we do have a horizontal asymptote at y is equal to 0, and that is our final answer for that. And so we won't do a whole lot with these, but we'll talk a little bit about how that impacts our graphs. Okay, all right. So for this function, this is a rational function. It says indicate where the function is increasing or decreasing, where there are any relative extrema. Remember, the relative extrema are our relative maximum, relative minimum, where these occur, where the asymptotes occur, where the graph is concave up or down, and where we might have any points of inflections or intercepts. So this is going to be a multi-part problem, and I'm going to actually start with the vertical and the horizontal asymptotes because we've just done that. We're also going to talk about the domain of this function, and we're going to talk about the intercepts for this function, and then we'll get into increasing and decreasing using the first derivative and concavity using the second derivative. So the first thing we're going to do is we're going to talk about the domain of this function. It's not asked us to do that, but it's very important because it is a rational function. So if you remember, the domain is going to be all real numbers except for any values that might make the denominator 0. So for this one, if I look at x minus 5 and I set this equal to 0, I find that x is equal to 5 is going to be a very special value. We're actually going to use this in a couple of places. So we can talk about the domain has to be all of these real numbers except for when x is equal to 5. And so when we list the domain of this function, it's everything from negative infinity to positive 5, and then we skip positive 5 and we jump from 5 to infinity, and that's actually my domain. Okay. For our vertical and horizontal asymptotes, let's talk about that vertical asymptote first. Remember, the vertical asymptote is the asymptote where we simplify the rational function. That was the first ones that we did. We simplify the rational function. We take the denominator and set it equal to 0. We've kind of already done that, so we're a little bit repetitive here. So to find that vertical asymptote, it is the equation x is equal to 5. So it is this equation, okay? So here we were finding the value that we had to remove from the domain. Here we're finding the equation, so it is this equation x is equal to 5. That corresponds to the fact that we don't have any values there, so this is kind of this where something strange is happening for us. The next thing we're going to do is talk about the horizontal asymptote. For the horizontal asymptote, this is going to be my equation y is equal to something. So if I think about this limit as x approaches either positive or negative infinity of this constant negative, we can put the negative on the top or in front, this constant over x minus 5, the power in the denominator is larger than the power in the numerator, and so this limit is going to be 0, and so our horizontal asymptote is the equation y is equal to 0. Now, y is equal to 0 is also known as the x-axis, so our graph is going to get very close to the x-axis, and it's not going to cross it. So we've done part of this. The only thing from this list before we start talking about derivatives are our intercepts. Now this is an algebra concept that we may or may not remember. So we can let x be equal to 0. And when we let x be equal to 0, this is going to allow us to find our y-intercept. And so when we let x be equal to 0, we find that, so that's another way to simply say we want to find f of 0. So I have negative 2 over 0 minus 5, and so I'm going to have a positive 2/5, and so that's going to be the point 0, 2/5. That's going to be our y-intercept. This function does not have an x-intercept, and you might be asking why it doesn't have an x-intercept, but it doesn't have an x-intercept because the horizontal asymptote is actually at y is equal to 0. Also, there's no way to make this function be equal to 0. So this function has no x-intercepts, right? Because y cannot equal 0. That's, like I said, another thing that this horizontal asymptote tells us, okay? All right, so the next part of this, we need to talk about intervals of increasing and decreasing, and so now we need to find the first derivative. So I guess we can call this part 5, however many parts you want to list. So we want to find this first derivative. Now to find this first derivative, we have choices. We can use the quotient rule. We can rewrite this. I'm probably going to go ahead and use the quotient rule for this. So the quotient rule, we start off with squaring our denominator. So we have x minus 5 squared. You can use low d high, you can use bottom derivative of the top, you can use f g prime, whichever way you remember to find the quotient rule. So my class, we did low d high. So we have the bottom part, so low is x minus 5 times the derivative of the top being negative 2, and that derivative is going to be 0, minus, and we take the high, which is our negative 2, don't lose that negative, and then the derivative of the bottom, or d low, is 1. So we clean this up, and this becomes a positive 2 over x minus 5 squared. I like the first derivative like this because we're going to talk about what this actually tells us. It tells us lots of things. So we're going to start by the critical values from this first derivative, or where the denominator is equal to 0, or where the derivative is undefined in this case. So we should not really be surprised that we have this critical value at x is equal to 5. I know x is equal to 5 is a problem. We're not actually going to have a point there because my function is not defined there. But that is possibly where something is happening here. So let's go ahead and put this on a number line and talk about this in terms of the first derivative number line. So if I put this on the first derivative number line, here's my 5, and maybe I select a value of 0, and I select a value of 6. Some of you are already guessing this, and you're like, why are we doing this? Well, we're just going through the motions here. What happens when I plug 0 in? I get negative 5 squared, which is positive 25. And for 6, when I plug 6 into my first derivative, I get 2 over 1 squared, which is just 1. Notice that, and we had this happen in a previous problem in section 3.2, this numerator is positive, this denominator is squared, and so it is always positive. My first derivative is going to be positive everywhere. So what this tells me is that this function increases. Now be careful how we write this. It increases from negative infinity to 5, and it increases from 5 to infinity. It does not increase at 5 because there's a problem. There's an asymptote there. The function's not defined there. So it does increase to 5 and then it increases again. What this tells me is that there are no relative extrema. So no relative extrema. So no maximums, no minimums, none of those things. This is kind of going to be a theme that runs through these rational functions. So I'm just going to tell you that up front. Kind of makes it nice. All right? All right. So let's move on to our second derivative to talk about concavity. So our second derivative, our f double prime here, once again, we can use the quotient rule. You can rewrite it. I'm going to use the quotient rule, so we talk about just remembering how to simplify and reminding you about the quotient rule. So it's going to be the denominator squared. When I square x minus 5 squared, I get x minus 5 to the 4th. Low d high, so my denominator is x minus 5 squared. Derivative of the numerator is 0 again because it's that constant, minus high. Now when I find the derivative of the denominator, it is going to be 2 times x minus 5 to the first power times the derivative of the inside, which is 1. So we've kind of got a good bit of stuff going on here. This is going to simplify and become negative 4 times x minus 5. You might be thinking, oh, we're going to have everything negative because I have this x minus 5 to the 4th power. That is not going to be the case because my second derivative simplifies to negative 4 over x minus 5 to the 3rd power. So I am going to have some changes in this because this is going to be negative and this is going to change. So critical value, same critical value, we still set the denominator equal to 0 because that is going to give us where we have possible changes at x is equal to 5. Once again, we can't make the derivative 0, but we can make it undefined. So I'm going to draw my second derivative number line. My second derivative number line again is going to have that same critical value of 5. I'm going to place these values on the number line. 0 is a very nice value. 6 is again a nice value. I'm evaluating the second derivative at each of these. So the second derivative at 0 is negative 4 over negative 5 to the 3rd power. Well, I don't really care what the number is except that it is going to be a negative. I believe it's 125. This is going to give me a positive value. And so this tells me that it is concave up on this interval. The second derivative evaluated at 6 is going to give me negative 4 over 1 to the 3rd power, which is going to give me a negative 4. More importantly, it is a negative value, so my function is concave down. Now this is a little bit misleading because I don't actually have a point of inflection. I do have a change in concavity, but no point of inflection. Somebody might be wondering why I don't have a point of inflection. Well, two things. One, if you plug 5 back in here, you would get 2 over 0 and you would know there was a problem. Also, if we go back and talk about the domain, 5 is not in the domain of the original function, so therefore I can't have a point there. So please note that there is a change in the concavity, and we'll write that out in a second, but there is no inflection point. And once again, there's no inflection point because there's no actual point at x is equal to 5. So taking all of this information that we have and our function, I'm going to move to the next page, which I've inserted so that we can draw the graph. There's just way too much information on here. So we are going to take all of this information, my function -2 over x minus 5. We have a vertical asymptote at x is equal to 5, a horizontal asymptote at y is equal to 0. Remembering this is also known as the x-axis, so our graph will get close to the x-axis and not cross it. We have a y-intercept at the point 0, 2/5. Increases everywhere, concave up from -infinity to 5 and concave down from 5 to infinity. So let's talk about how we would go about graphing this. And the nice thing is that even on your homework and your quiz and your test, this graph will be a multiple choice. I'm not going to ask you to graph. That's kind of challenging to do. I am going to ask that you be able to recognize lots of different features on here. So let's look at this first thing. So we're going to look at the point 0, 2/5. So let's go ahead and let's just get a couple of points on here, a couple of x values. I do want to go all the way out here to x is equal to 5 because that's going to be useful to us, and get a couple of points here and a couple of points down here on our negative y-axis. Don't really need anything, but we'll put that over here. So at 0, 2/5, so this is going to be, let's change colors here. So 0, 2/5, that means I'm going to have a y-intercept somewhere about in here. That's not perfect, but it's kind of close. So let's draw our vertical asymptote here. So we have 1, 2, 3, 4, 5. And so I'm going to make this a little bit of a different color here and see if I can get it to kind of go through here. So this is actually our vertical asymptote, and we're going to use that to tell us kind of what our graph gets close to here. We do know that it increases until it gets to 5, so that means it's going up because here is our horizontal asymptote along this line, so it's going to get really close to this, but it's not going to quite touch it. It's going to get close to this vertical asymptote, and it's concave up on the left side of this vertical asymptote. So what happens, and you can plot a couple of points in here if you want to. If you want to let x be equal to 1, let's say, for example, if you wanted to plot one extra point, let's say if we let x be equal to 1, then this would give us -2 over -4, which would give us a positive 1/2. So we would be somewhere about here. Doesn't give us a great idea, but we get sort of an idea of which way this graph is headed. So the more points you plot, the more closely your graph might actually resemble the correct graph, but you get a good idea. So what I want you to recognize is that this horizontal asymptote is going to act like a kind of an attraction. So it's going to attract this line, but it's not going to actually cross it. Okay, so that's part of our graph, but we do know that the concavity changes and becomes concave down. However, the graph is still increasing. And so on the right side of this vertical asymptote, what my graph is going to do, and once again, if you wanted to pick a point, so at x is equal to maybe 6, let's see what happens. That's over there to the right side. This would give me -2 over 6 minus 5, or -2 over 1, which gives me a y value of -2. So here is a point, gives you a little bit of an idea of what's happening. Once again, it's going to get very close to that asymptote, and it's going to get very close to this asymptote, but this is going to be what the graph looks like. It's called a hyperbola, so you may have seen these before. Rational functions typically have this kind of shape. So what I need you to recognize is, where is the vertical asymptote, where is the horizontal asymptote, where is the intercept. Notice that it's increasing in both of these intervals. It is concave up on this interval and concave down on this interval. So you're going to be recognizing the shape of graphs. All right? Okay. Let's move on to another one of these. So same process, lots of pieces in here. We'll start with the domain of the function. So the domain is what we're going to be looking at. For this function, we only have one place where the denominator is 0, and that is where x is equal to 0. This must be removed from my domain, and so the domain is negative infinity to 0, and then union 0 to infinity. When we talk about the domain, we talk about both intervals, and that's why we use that union symbol. Vertical asymptote, remember vertical asymptote again is where we take the denominator and set it equal to 0. So that's kind of nice. That is my vertical asymptote. X is equal to 0. Not a whole lot else I can do with that. So that's going to be here. My horizontal asymptote, this is where we're looking at the limit as x approaches infinity. So the short version of this is to say, okay, y is equal to, they have the same highest power is in the numerator and the denominator. The degree of the numerator is 1. The degree of the denominator is 1. Means the same thing. So I take my coefficients, which is 3 over 1. I am going to simplify 3 over 1. And so my horizontal asymptote occurs at y is equal to 3. Okay. So for the y-intercept, recall that we let x be equal to 0. So we're going to say, all right, let's let x be equal to 0 here. When x is equal to 0, then f of 0, we have a problem. 0 minus 1, this does not exist. So we have no y-intercept. You might have recognized that because we have a vertical asymptote at x is equal to 0. So no y-intercept. So I wanted you to see that as we worked through that. So no y-intercept. There's nothing wrong with that. So let's talk about the x-intercept for this function. The x-intercept is what happens when the function is equal to 0. So we didn't have this one before. So in this case, we want to say, all right, let's take 3x minus 1 and over x and set this equal to 0. Now, in order for a rational function to be 0, it's not the denominator that's equal to 0, because that's where we have issues and that's where we have domain issues. That's where we have our vertical asymptote. But we can take the numerator. So we're going to set 3x minus 1 equal to 0. Any value that makes the numerator 0 makes the fraction 0, and we add 1 to both sides and divide by 3. And so we do have an x-intercept for this function, and it is at the point 1/3 0. So that's a little bit different. Okay. All right, so the next thing we're going to do is to talk about that derivative, the first derivative of this function. So our first derivative is going to be, once again, I'm going to go ahead and use that quotient rule. So it's the denominator squared of the original function. So the bottom times the derivative of the top, which is going to be 3, minus the top function times the derivative of the bottom function, which is going to be 1. We do have to clean this up. This is going to be 3x minus 3x plus 1. So this is going to clean up to be relatively nice first derivative. 3x minus 3x simplifies, and so I end up with a first derivative, which is going to be 1 over x squared. Now, you might be recognizing that 1 over x squared is, yes, it is always positive. 1 is always positive. X squared is always positive. So even if I were to set x is equal to 0, so the critical value from this comes from setting the denominator equal to 0, even though it can't be a point on my graph because this particular function has a problem at 0. The function's not defined. It's not in the domain. There's a vertical asymptote, all kinds of things that tell us problems here. But once again, even if I were to put this on a number line, that's a terrible looking number line. Let's see if we can draw that a little bit nicer. So my first derivative number line, just to give you that idea and kind of consistency in this, if I put 0 here, I know what's going to happen. If I plug in a negative, that first derivative is still going to be positive. If I plug in a positive, that first derivative is going to be positive. You can write it out if you want to. Negative, this is going to be a positive value. The first derivative at 1 is going to be a positive value. So it increases, and that's what we would say about this function. It increases. Again, we have to skip that value of 0. So, oops, let's just try that again. So I think my pen's skipping and it's making my brain skip a little bit. Negative infinity to 0, and then it skips to 0 and goes to positive infinity. So it increases everywhere, jumping that value of 0, but no extrema. So no maximums, no minimums, so no extrema for this function, okay? So then the next part we're going to do is the second derivative. So the second derivative of this function, relatively nice because I have this x to the 1 over x to the second. So I'm going to actually go right up here and rewrite my first derivative. This was an early derivative rule that we used and technique we talked about. 1 over x squared we could rewrite as x to the negative 2. Makes finding that second derivative a little bit nicer. So I have negative 2 x to the negative third power, and I can rewrite this as negative 2 over x to the third power. Really want it in this format when we start talking about those critical values and finding the intervals of concavity. Once again, I'm going to have that something funny happens here at 0, that critical value. So for my second derivative number line to talk about concavity, I can still put 0 on there. Negative 1 works very nicely, positive 1 works very nicely. The second derivative evaluated at negative 1 is going to give me negative 2 over negative 1, because when I cube negative 1 I still get a negative. This is going to give me a positive value, so my function is concave up. When I evaluate the second derivative at positive 1, I have negative 2 over positive 1, which gives me a negative value, so we can say that the function is concave down. So again, concavity changes at 0, but there is no changes, but no inflection point. Again, the reason for no inflection point is that there is no actual value, there's no point when x is equal to 0, because I do get negative 1, but I get negative 1 over 0, and that's a problem, okay? So we'll move to the next slide so that we can put some more information over there, and we will sketch the graph of this. All right, so we're on a new page here where the graph, we're going to graph the function 3x minus 1 over x. The domain, remember, is negative infinity to 0 and 0 to infinity. We have a vertical asymptote at x is equal to 0. This is actually my y-axis, so my graph is going to get close to my y-axis but not cross it. Horizontal asymptote at y is equal to 3, no y-intercept, and an x-intercept at 1/3. And we know it increases everywhere, concave up, and then it changes to concave down. So in this case, so our vertical asymptote is the y-axis, and so I'm not going to actually draw it, but it's going to get close to this. I am going to put on here our horizontal asymptote. So, and so we're going to go all the way up here to y is equal to 3, and then I'm going to draw us a nice little dotted line at y is equal to 3. It's going to go through here. That's approximately y is equal to 3. I'll move that down just a little bit and to right there. And so this is going to be our horizontal asymptote where our graph is going to get close, but it's not going to quite touch it. We're going to go ahead and graph the one x-intercept that we have. So let's put a couple of kind of reference points on here. We're going to have 1, 2, 3 gives us an idea, and so at an x value of 1/3 and a y value of 0, remember that's what our x-intercept means, this is going to be our graph. Again, it's going to get close to this line, it's not going to cross it. I do know that on the right-hand side of 0, it's going to be concave down. On the left-hand side of 0, it's going to be concave up. I do know that it increases everywhere. Again, you can pick some x values. For example, if I pick an x value of 1, if I let x be equal to, or let's go with negative 1, let's go over here to this side. X is equal to negative 1, that's going to give me negative 3 minus 1 over negative 1. So I would get negative 4 over negative 1. I would get a y value of positive 4, so I know I have a point at negative 1, positive 4, so somewhere up here above my horizontal asymptote. So my graph, again, is going to be really close to this, and it's going to get close to my y-axis, but it's not going to cross it. So I see that it's increasing in concave up. On the right-hand side of my y-axis, it's going to be really close. It's going to come up here, and it's going to get close to this horizontal asymptote again, close to the y-axis or my vertical asymptote. Same thing, it's increasing, but now it's concave down. Again, this will be a multiple choice graph, and so you're going to be looking to identify the horizontal asymptote, the vertical asymptote, the intercept, the fact that it's increasing on both sides of this, and that it is concave up on this side and concave down on this side. And that's what you're going to be looking to address and pick out in those graphs, okay? So keep that in mind. So one last problem, and it is an application problem. So if you want to pause for a second, think about graphs for a second, and then resume, but this is the last problem in this section. Okay, so for an application problem, cities and companies find that the cost of pollution control increases along with the percentage of pollutants being removed. Suppose the cost C in dollars of removing P% of the pollutants from a chemical spill is given to us by this very nice rational function. Yes, so where P cannot be equal to 100, that means that they can't remove 100% of the pollutants. That doesn't make a whole lot of sense. So I mean, it does make a whole lot of sense. So anyway, so we'll address that as we get to it. So the first thing we're going to look at is to find these two values, C of 0 and C of 80. So we're simply plugging, these are what I call plug and chug problems. So C of 0 means that I'm going to plug 0 in for our value of P. So I have 48,000 over 100 minus 0, or I have 48,000 divided by 100. Nice thing about dividing by 100 is my zeros cancel out, and I get 480. All right, so this is C of 0. We're going to talk about what that means. All right, and then the second part of this first thing, and then we'll talk about what they both mean at the same time, is going to be, we're going to be plugging 80 in for P, and so we're going to have 48,000 over 100 minus 80, which is going to give us 48,000. Oops, sorry, my pen doesn't want to write. 48,000 divided by 20, and that is going to give us a very nice value of 2,400. Okay, so what is this actually telling us? Well, it's telling us that because C is cost in dollars of removing these pollutants, the percentage of pollutants, so the cost of removing 0% of the pollutants is $480. Okay, so they don't remove anything, it's going to cost $480. All right. There's probably startup costs and things like that included in all of this. To remove 80% of the pollutants, it's going to cost $2,400. Okay, I mentioned a while ago when we started with this problem, I mentioned that the fact that P couldn't be 100. So when we start talking about the domain of this function, so the domain of this we're going to find by taking that denominator and setting it equal to 0. So that's why we really kind of pointed that out to you to begin with. So we take 100 minus P, set this equal to 0, and we discover that P is equal to 100. Subtract 100, divide both sides by a negative, however you want to go about that. So the domain of this function is actually a little bit, we have to be careful here, is 0 to 100, and we stop here. Now, why is it not negative infinity to positive infinity? Well, can we remove negative percents of the pollutants? And the answer is no, probably not. So percentages need to be positive numbers, and so we can't remove negative percentages. We also can't remove more than 100% of the pollutants, and so that's why it's going to stop at 100. So our domain falls between the values of 0 and 100, not including either one of those. We could include 0, so we'll put a square bracket around 0 because we can actually include 0. We even found 0 a while ago. So our domain goes from 0 to 100, but we do have to stop at 100. Okay. All right, so the next thing we want to do is to talk about the graph of this function. So we're going to use some things that we've just talked about in the previous sections. So we're going to start by talking about, we've looked at the domain of this function. So we want to find vertical and horizontal asymptotes. We do have a vertical asymptote, at P is equal to 100. So here is our vertical asymptote. We have a horizontal asymptote we can find, so we'll actually call that C because that's what our Y value is. So at C is equal to what? So let's think about this. We have a power of P in the numerator is 0 because there is no power. Power of P in the denominator is 1. The degree of the denominator is larger than the degree of the numerator, and so typically our horizontal asymptote would have been y is equal to 0. So we can say that our horizontal asymptote in this case is C is equal to 0. Okay. Let's talk about the first derivative and what that's going to tell us. So the first derivative for this function, so that should be C prime of P. All right. The denominator is squared, so 100 minus P squared, and so we have the bottom function times the derivative of the top, which is 0 because it's a constant, minus the top function, which is 48,000, times the derivative of the bottom function. Watch that, that's negative P. Be very careful there. All right, the derivative of the denominator is not negative P, negative 1, sorry. I was worried about the negative sign and forgot to change that to a 1. So the derivative of the denominator is negative 1, all right? And so my derivative then is positive 48,000 over 100 minus P, where this quantity is squared. You notice anything consistent about this in the other ones? It is always positive. So the first derivative of this function is positive everywhere. So it is always positive. Now, we don't have to worry about jumping over 100 and making it anything like that, so we can say that it is positive from 0 to 100 because that's what we're worried about. It's not actually positive at 0. Typically we use these open intervals. So we know it's positive everywhere, so we know it's increasing everywhere, and so it's going to go up. So the cost, and that does make sense, the cost increases as the percentage of the pollutants is removed. So that kind of does make sense. Let's go ahead and find the second derivative just to help us sketch the graph just a little bit better, and then we'll talk about the graph of this. Keep wanting to make that an X there, sorry. All right, so again, we're going to have that denominator. So our denominator, and then the derivative of the numerator is 0 minus the top and the derivative of the denominator. So we are going to have this in here times the derivative of the inside, which is that negative 1, and all of this is over that denominator squared, which is going to be, sorry, my pen is wanting to be very herky-jerky right this minute. I apologize for that. Usually this happens when I'm standing up in front of the classroom and I'm far away from the podium, and I'm not far away from the podium on this one, so it's okay. All right, so as we clean this up, the first part goes to 0, negative and negative is going to become positive 48,000. Oops, sorry about that. Let's go ahead and multiply 48,000 by 2, and so that's going to be 96,000 positive, and then 100 minus P over this denominator, and we are going to be able to simplify that to let our second derivative be 96,000. Oops, sorry. I think my brain kind of stopped here. Over 100 minus P to the third power. All right, so this is our second derivative of this cost function evaluated at P, the percentage. All right, so we do know that we're probably going to have a change in concavity, but that change in concavity is going to occur around 100. So we really are only concerned about what happens to the left of 100. So we can once again, we can talk about this second derivative, and I'm really only concerned about what happens over here. So let's plug in 0. If I have 0 plugged into this second derivative, it is going to give me a positive value. So it's concave up, right? So that's what we know about this graph. So we're going to have just a really very small sketch on my graph over here. I really just need these two quadrants here because we're only talking about values that are from 0 to 100. And so we'll start here. And we know that at 0 that my y value or my cost value, so this is my cost, is going to be 480. So at 0 I have this value here. I know out here at 100 I'm going to have this line that the graph gets close to but doesn't cross, and I do know that at 80 it's going to jump up to 2400. So again, it's not going to be a perfect graph, but we're going to get an idea. It is going to increase and it's going to continue to increase. We'll move that, and then it kind of shoots off up here. We'll make that point a little bit bigger. So it's not going to ever actually cross this 100 mark, but it is going to look something like this. That's not a perfect graph, but it's close enough so we can identify that. The last part says, can the company or city afford to remove 100% of the pollutants due to this spill? Well, it looks like the cost is going to become literally astronomical. So when we talk about the limits, as x goes to 100, or as p goes to 100 for this function, that's where that horizontal asymptote comes in. And so we're saying that we're not going to be able to do this. So excuse me, not my horizontal asymptote, but the limit as p goes to 100 becomes infinity, and so we're not going to have, that's where my vertical asymptote comes in, we're not going to have, the cost is going to be astronomical. So the answer to this question is, can the company or city afford to remove 100% of the pollutants? And the answer is no, they cannot. The cost just becomes astronomical. So, all right. Hopefully that makes sense. That's a little bit kind of a strange question, but nice application problems, and hopefully that will help you with your homework questions and quiz questions and possibly test questions. So that ends the material for section 3.3, and I hope you have enjoyed business calculus. Bye-bye.